Welcome back, friends. In this video, we will be discussing about betweenness centrality in detail. The betweenness centrality in a network analysis is a measure of the entity's importance, and it is basically a node or an edge which acts as a bridge in the network. So we try to identify these bridge elements. This is done by quantifying how often the element lies on the shortest paths between nodes. Though we are going to talk about the quantification of the shortest paths, the calculation for node and edges, there's a slight difference in the formula. We will first look into the node betweenness centrality and then following that up with edge betweenness centrality. When we talk about node betweenness centrality, the betweenness centrality quantifies a node's influence over the flow of information, right? The nodes that facilitate information flow. And it basically acts as a bridge. That is very important, right? So it is trying to connect two different networks as a bridge. The mathematical part of it is basically we try to look at the number of shortest paths a node is lying between any pair of nodes. We try to count all those shortest paths and then we try to aggregate that, which gives us the measure of betweenness centrality. This basically helps us revealing the nodes that basically try to help us connect with different clusters. There is a big network, but within the network, we will have clusters, right? So these nodes, which act as bridge, connect these clusters together. Now, let us try and look into the math part behind it, and then we'll automatically understand the practical applications of it. So when we talk about node betweenness centrality, right? So let us try and assume a simple network. Okay, you can draw any kind of a network. Let's assume that we have a network like this. Let's say this one is connected. Okay, so let's say this is our network. This seems to be one cluster. I will draw a similar cluster. Let's say I'll take three nodes, and these three are connected together. Okay, now let us assume that there is another node here which is helping us connecting these nodes. Okay, this is our network, simple network. Let's try to imagine any network. So one, we'll say two, three, four, five, six, seven, eight, nine. So let us label these nodes. Now we want to identify the betweenness centrality for these nodes and identify which node has the highest betweenness centrality. In order to deal with this, from a visual inspection, we can clearly see that this particular node, node 4, seems to be having high betweenness centrality because it is trying to map or connect two different clusters in itself. Let us assume that. So let us try and identify how do we calculate betweenness centrality for this one node, and the same calculation holds good for all the nodes. Now, the betweenness centrality is explained as the sum of the number of shortest paths, the number of shortest paths between pairs, between a pair. Okay, that specifically is passing through node 4, that pass through the node of interest. What is the node of interest in our case? It is 4. So we'll specifically write the formula for node 4. So this is a numerator. We are trying to find out the shortest paths between any pair of nodes but that path should pass through node 4 divided by the total number of shortest paths. All the shortest paths between the pairs, between the same pair of nodes that we are talking about. Now, how do we actually quantify it? So let us try and assume the two clusters. So let's say this is cluster A, this is cluster B. Assume. Okay. So what I'll do, I'll take a table here. I'll say cluster A nodes. These are basically 5, 6, 7, 8, 9. And here I will take cluster B records or cluster B nodes. I have 1, 2, 3. Now let us try and detect the shortest paths between these pairs. 1 to 5, 1 to 6, 1 to 7, 1 to 8, 1 to 9. Likewise 2 to 5, 2 to 6, 2 to 7, 2 8, 2 9. And so on and so forth. So let us first detect 1 to 5. Let us calculate 1 to 5. So when I say 1 to 5, what is the shortest path that we can think of? This is 1 and this is 5. Shortest path is basically the number of traverses through the nodes that we are making. So here I can think of 1 to 3, 3 to 4, 4 to 5. This is one path that we can see. There's another path which is 1 to 2, 2 to 3, 3 to 4, 4 to 5. So there are only two outgoing connections from node 1, right? Two connections on node 1. So using these two, we are trying to frame the paths. And what we can see is this is the shortest path. This is not the shortest path. We only need the shortest path. So here I have one shortest path. So denominator in this case is 1. But does this shortest path pass through the node in question, which is node 4? Yes, it is. So we will have 1. So we will write 1 here. This is the calculation for 1 and 5. Similarly, I'll have to look at 2 to 5, my bad. We will say now node 2 to 5. Let's stick to 2 to 5. So from 2 to 5, I have to calculate. Again, from 2, there are two connections. One is this one is this one. So 2 to 3, 3 to 4, 4 to 5. 2 to 3, 3 to 4, 4 to 5. The other one is 2 to 1, 1 to 3, 3 to 4, and 4 to 5. So again, I have only one shortest path from 2 as well. Then we will look at node 3 now, 3 to 5. The 3 to 5 connection is only one connection is there. If I have to traverse, I can also traverse 3 to 4, 4 to 6, and then 6 to 5, but that is not the shortest path. So here also I am taking 1. Now let us move on to 1 and 6. So here I will erase this and then we will try to write 1 to 6 path now. 1 to 6. What are the shortest paths that we can think of? 1 to 3, 1 to 3, 3 to 4, 4 to 6. 1, 3, 4, 6. This is the shortest path again. We don't have alternate. This is again is going to increase one additional value. So this is 1. Then we will talk about 2 to 6. From 2 to 6 also I have 3, 4, 6. So this is also going to be 1 because this is passing from 4. Likewise, 3 to 6. This is 1, 2, 3, 4, and 6. This is the only path. Next comes 1 to 7. From here on, little complications will increase. Let's observe. So from 1 to 3, 3 to 4, I'm calculating for 1 to 7, right? So 1 to 3, 3 to 4, 4 to 5, 5 to 7. Again, 1 to 3, 3 to 4. Then from 4, we can also go to 6. And from 6 also, we can go to 7. So here, I would be getting two paths which are passing through node 4. And those are the only two shortest paths that we can compute. So again, we will get what? 1. Likewise, from 2 to 7, if you calculate, you'll get 1. So on and so forth, we will have to calculate for all the nodes. And what we observe is this node 4 is at the center of passing through all the nodes, right? It is basically passing through all the nodes. So I'll have to compute all the values like this. So how many ones are there? 1, 2, 3, 4, 5. There is 15. So my betweenness centrality for node 4 is 15. This is how we compute. If you take any other node, right? Let's consider node 6, for example, as our node of interest. Okay. Node 6. This is what I want to compute. So if I take node 6 as my node of interest, I will have to again compute 1. Let's say now my cluster would change, right? The shape of my cluster would obviously change here. So what I'll do is I'll take 4 can be taken into that cluster A, or I can take that 4 into cluster B. Anyways, okay, this is my two clusters that I'm dividing. Okay, either way you can define it. So 1, 2, let's say 4. Now I'm calculating 1 to 4. So this is 1, this is 2, this is 3, 4, right? So if I say 1 to 4, then I have one shortest path. But is that shortest path passing through node 6? No. So this becomes 0. Likewise, if I have to compute, let's say 1 to 8, if I have to compute node 1 to 8, in this case, the shortest paths can be 1 to 3, 3 to 4, 4 to 6, 6 to 8, right? This way. Can I have any other path? Let's see. 1, 3, 4, 5, and then it has to go to 6, 7, right? So this is not the shortest path. 1 to 8 is, again, we are getting 1 only. What if I take 7? Let's say 1 to 7 is there. So if I say 1 to 7, then I'll take 1, 3, 4, then we have 5 and 7. This is one path. 1, 3, 4, 6 and 7. So there are two shortest paths, and out of this, one path is passing through the node of interest, 1 by 2. This way we compute all the centrality measures, betweenness centrality measures for each pair, and then aggregate that. We add all of them. This basically is our betweenness centrality measure. It basically helps us identifying the critical nodes. For example, if I have to look into the transportation, right? In a transportation network, it could be either bus transport or air transport. The nodes with high centrality are critical points, right? They basically have the junction. We can talk about them as the junctions of the entire network. It helps us to identify the bottlenecks as well. All right. So these are some of the examples that we can think of. Like we can also talk about, let's say, social media network. Who is the most influencer person? Right? He basically that person would influence many cluster nodes. In biological systems, we talk about the essential proteins. Right? In protein interactions, the nodes with high betweenness centrality, they can be identified as the essential proteins that are critical for the entire biological process that happens. In fraud detection, for example, which are these the nodes which are acting as bridges between clients, and We can identify if they can be the potential right cases of people who can commit frauds. Smart cities, if I talk about smart cities, right? Cities connecting various routes. So you will have a junction, right? Intersections. Betweenness centrality can be imagined as the intersection there. This basically is a quick intro into node betweenness centrality, friends. In our next video, we will talk about edge betweenness centrality, which is one of the essential computation that goes into the community detection algorithms that we have seen previously, Girvan-Newman algorithm. So it's an essential computing component of the Girvan-Newman computation. So we'll see edge betweenness centrality in the next video. Thank you. Hope you enjoyed. I'll see you around.